In the last class, we studied about Laplace transforms, introduction about Laplace transforms. So we said that Laplace transforms are denoted by capital F of S, and also it is Laplace transform of f of t, small f of t, which will be nothing but rho to infinity e raised power minus st f of t dt, right? So this was the definition of Laplace transform. Then I introduced you to Heaviside functions. So Heaviside function. The definition of Heaviside function is, let's say it is denoted by u of t minus a, where its definition is it will be 0 when t will be less than a, and it will be 1 when t will be greater than a, right? So if I plot the graph of this function, like it is 1 here, this is u of t minus a, and this is a, and this is time axis. So before a it is 0, and after a it is 1. It will look something like this. After a it is 1. Okay, before a is it is 0. So I told you that it is used, this kind of function is used in many applications, such as activating or deactivating some forces. So let's say there are some, so let's say there is a structure. I told you that there is a structure and a ball, some object. So let's say this is a structure, or some overhanging structure is there, and a ball is hitting the structure, and ball comes and stick to the structure. So initially the force was 0 when the ball was in the air, stick to the structure, then there will be sudden activation of the force. In these kind of applications, these Heaviside functions are used where there is sudden activation of some forces. Now, I also discussed about Laplace transform of this Heaviside functions. So that will be, just use the definition of Laplace transform, e raised to power minus st f of t, which is u of t minus a here, and then dt. So u of 2t minus a is 0 up to a, so we can split it from 0 to a. So minus st, 0 to a, this is 0, and time will always starts from 0, that's why I'm starting from 0 to a. And then a to infinity is, it is 1, right? U of t minus a is 1. If you now integrate this, so finally you will get e raised to power minus as by s. So that is the Laplace transform of your Heaviside function that we studied. Now, we also studied about first shifting theorem. So does anyone remember what was first shifting theorem? So it was the shifting in variable s. So first shifting, we also called it as S shifting, right? So just, so it was like, let's say we have Laplace transform of f of t denoted by f of s, right? Then if we want to calculate Laplace transform of, if you want to calculate Laplace transform of e raised to power at f of t, its f of t is multiplied by e raised to power at, then its Laplace transform will be nothing but f of s minus a. So in this function f of s, just replace s with s minus a. You need not to calculate this integral again. Okay. Similarly, there is second shifting theorem. Which is known as t shifting. Now there will be shifting in time variable, not s variable. So the second shifting theorem will be like this. Let's say you have Laplace transform of f of t is capital F of s. Then You want to calculate Laplace transform of f of t minus a multiplied with u of t minus a. Okay. So now what you have done is, firstly you have shifted the time from t to t minus a and multiplied this with the Heaviside function. That's what you are doing in this case. So then the Laplace transform of this quantity will be e raised to power minus as f of s. That's it. You need not to evaluate. If you know the Laplace transform of this function f of t, then the Laplace transform of f of t minus a into u of t minus a, where this u is nothing but a Heaviside function. So minus as into f of s. That's very easy to prove. So let's prove it. So we'll start with the right hand side. So right hand side is e raised to power minus as f of s, and f of s is nothing but Laplace transform of f of t, right? Of Laplace transform, it was e raised to power minus as and integral 0 to infinity e raised to power minus st f of t, right? That is the definition of Laplace transform. Now we will solve this one. So I'm taking e inside the integral, so it will be t into s f of t dt. And so instead of t, let's use the variable tau for the time being. I mean, you can use any variable. So if t, I want to use tau. Doesn't matter because I'm consistently tau everywhere. Okay. So also you can just write. I'll just replace t with tau. It's fine. So here also, because later on I will use t, so that's why here I'm using tau. Now I want to put a plus tau is equal to t in this integral. In this integral, what I'm going to do is going to 0 to infinity. So I will put a plus tau is equal to t. So now this implies a is a constant, so d tau is equal to dt. That is fine. But the limits will change. So when tau is 0, t will be a, and when tau will be infinity, t will be infinity. So finally, this integral will be changed to 0, a to infinity, right? A raised to power, e raised to power s into t, and then f of tau will be what? F of tau will be f of t minus a, right? Because tau will be equal to t minus a, and then d tau will be equal to dt. Finally, what we can say is we have this s for minus st f of t minus a dt. But we want to get this, right? So Laplace transform goes from 0 to infinity, not a to infinity. So what I will do is I will just multiply. So let me just write it in some other way. Can I write this a to infinity as 0 to a, and I'm multiplying u of t minus a f of t minus a e raised to power minus st dt plus a to infinity u of t minus a t minus a e raised to power minus st dt. Well, we written in this form. Yes, it can be written. Can be written in this form because when t is less than a, u of t minus a is 0. So because here the limit of time is going from 0 to a, where t is less than a, so this will be 0. It doesn't matter. When t is greater than a, this is 1. So this whole thing will, this will be 1. That's the 0 plus this quantity will be equal to this quantity. Right? Still anyway be equal to 1. So write it like this, then I'm combining because these two functions are same. I can just combine the limits. So finally it will be 0 to infinity. U of so now this can be written as this is nothing but Laplace transform of u. Here from this. So it is here, it is at this point when we need to convert this integral from which is going from a to infinity to 0 to infinity. Then only we need this heaviside function. Okay? So second shifting theorem is proven. So whenever we have to calculate f of t minus a and u of t minus a, then we can use this. Yes. So I'm just writing it here. So this is this second shifting theorem. Note down this formula. We will use it very frequently. First form of second shifting theorem, which is L of um, you can also write it like so. If you substitute f of t minus a, let's say f of t minus a, saying that let f of t minus a is equal to g of t, right? 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 So then this implies f of t will be equal to g of t plus a, right? Only what we can get. If you put this formula, so finally you can get L of g of t, right? And then this can be equal to e raised power minus as, and f of s was nothing but Laplace transform of f of t, which is g of t plus a, right? So, and then again I can convert this g of t, g with f, right? Any function can be denoted with any letter. So I'm just replacing this g with f again. So finally I can write just a letter replacement. So I can just write u of t minus a f of t Laplace transform of f of t plus a. You have a function f of t and its Laplace transform is capital F. Then the second shifting theorem will result in e raised power minus a s f of s. It means you have to shift your function also with a, and then you have to multiply with a shifted heaviside function. But let's say if you want to keep your function same, so let's say your function is f of t, but you are multiplying it with a shifted heaviside function, then it will be equal to e raised power minus es and Laplace transform of form of f of t plus a. Uh, this can be demonstrated with an example. It makes your job easier. Let me tell you how. So let's say I give you a function. So let's say this function is f of t, which is given as, so this function is 2. t square by 2. Please ask questions if you have any doubt in between, okay? Please stop me and ask questions. Okay, so t square by 2, if find Laplace transform of f of t. First of all, you have to convert this function into a single function using Heaviside functions. Right? So can you tell me what will be equivalent value of f of t in terms of piecewise function, right? Piecewise, because it is defined in a piecewise manner. Now I want a single function. Tell me. Is anyone smart enough to do it? Yes, Ariba, can you tell me? Or Athar? Then do it for you. So this 2 is, and time will anyway go start from 0. So time is anyway is positive quantity starting from 0. So I'm multiplying this 2 with Heaviside function uh, u of, because when t is less than 1, this value will be 0, right? So this will result in 2 multiplied by 1 is equal to 1. But when t will be greater than 1, this value will be 1 and this 2 will be 0, right? This quantity is only active from 0 to 1. Then I'm writing t square by 2, and then the next quantity, which will start from 1. So u of t minus 1 minus t minus pi by 2, because uh, this quantity when t will be less than 1, because this is also negative, this is also negative, so this will be 0. When t will be greater than 1, then this quantity will be activated, this will become 1 and this will be 0, so it will become t square by 2. And then when t will be greater than pi by 2, then this will also get activated, so this will be 1, this will be 1, this will go to 0 again. So this will be active only when t is going from 1 to pi by 2. Plus, can you tell me the last term? Sine of t, what should be here? It has to be activated only when t is greater than pi by 2. What should we do? Should we multiply it with which quantity? Just tell me what should be the form of Heaviside function. Zaira, can you tell me? T minus pi by 2. because when t will be less than pi by 2, this will be 0. This has to, this will not be active, and when t will be greater than pi by 2, this will be 1. So this will lead to cosine of equivalent form of above piecewise function. So we can convert any piecewise functions into a single, into an equivalent single function in terms of Heaviside functions, right? So now let's say we want to find the Laplace. So your task is find the Laplace transform. So you have to find this. So solution starts from here itself. Transform f of t, right? So that will be, so Laplace transform of, which will be Laplace transform of 1. So you have to refer this table which we discussed in the previous class. So Laplace transform of 1 is 1 by s. So here I'm writing 1 by s. And what will be Laplace transform of u of t minus u of t minus 1. So if you remember, Laplace transform of u of t was e raised power minus as by s. And obviously this is 1, right? So a second shifting theorem, can we apply second shifting theorem here? No. So there's no need because it's directly u of t minus 1. So Laplace transform of u of t minus a was e raised power minus as by s. So that's why here also Laplace transform of u of t minus 1 will be e raised power minus a is 1, so s by s, right? Plus then you have Laplace transform of e square by 2 multiplied with u of t minus 1, right? Then minus you have Laplace transform of t square by 2 u of t minus pi by 2, right? Then you have Laplace transform of sine of t multiplied with u of t minus pi by 2. So we are going to use second form of second shifting theorem, this one. L of u of t minus a f of t is equal to e raised to minus as f of t plus a. So L of u of t minus a f of t e raised power minus as Laplace transform of f of t plus a. Right. So this is the form. So finally, so firstly we will evaluate this quantity here, this one. Okay. So Laplace transform of t square by 2 u of t minus 1. So it is multiplied. So this is your f of t, and this is your multiplied with u of t minus a. So that will be equal to e raised power minus a. A is 1, so s is minus s, and Laplace transform of t plus a, which means t plus 1 to the whole square by 2, right? Because here you have t square by 2, f of t is t square by 2, so f of t plus 1 will be t plus 1 to the whole square by 2. So finally you can take out 2 outside, and then you have Laplace transform of t plus 1 to the whole square. So t plus 1 to the whole square can be written as t square plus 1 plus 2t, right? And then you have e raised power minus s divided by 2. So Laplace transform of t square will be, you see here, Laplace transform of t square will be 2 by s cubed, right? So I'm writing here just transform of 1 will be 1 by s again. Then Laplace transform of t will be 1 by s square. That's what I'm writing here. So finally, this is the answer. So I can just take 2 inside. So finally, it will be 1 by s cube plus 1 by 2s plus 1 by s square. So this is Laplace transform of t square by 2 into u of t minus a. This second shifting theorem has made our job very easy. Now let's do for this part here, L of t square by 2 u of t minus pi by 2. So this is the same thing, only thing is our a is now pi by 2. Okay, so then it will be e raised to power minus as, which is pi, a is pi by 2, so pi e raised to power minus pi s by 2. Then in the same thing we have to do t plus pi by 2 to the whole square, so not 1. Right, so you have to find Laplace transform of this quantity. So we have applied Laplace transform of f of t into u of t minus a, which is equal to e raised to power minus as. A is pi by 2, so e raised to power minus pi by 2 s into L of f of t plus a, so f of t plus pi by 2 squared by 2. Finally, you can just write e raised to power minus pi s by 2 divided by 2, and Laplace transform of e square plus pi square by 4 plus pi t, right? Yeah. So we know that transform of t square is 2 by s cube, and Laplace transform of pi square by 4 into 1, so it will be 1 by s, and then Laplace transform of t will be 1 by s square, right? So finally we can take this 2 out inside, so you'll get, finally we'll get 1 by s cube pi square by 8s plus pi. Now we have to find Laplace transform of the last quantity, which is cosine of t of t minus pi by 2. So Laplace transform of cosine of t and then of t minus pi. So finally we can again apply second shifting theorem. So now your f of t is cosine of t and u of t minus a. So t minus a is pi by 2. So again e raised to power minus as, which is e raised to power minus pi s by 2, and then pi by 2. Sine of t plus pi by 2 is minus sine pi by 2. So minus sine t, it will be not pi by 2. So finally we get minus of e raised to power minus pi s by 2 Laplace transform of sine t. And we know that Laplace transform of sine t, now we have all Laplace transform of all the quantities. So here we have Laplace transform of this first quantity, then the second quantity, third and fourth. So if you put all the values in this expression, so finally we will get the Laplace transform of the complete function. Function. So this will be 2 by s minus 2 uh, by s to the power e to the minus s. That is for first function. Then for second function we have from here, which is e raised to power minus s 1 over s cube plus 1 over s square plus 1 over 2s, and then e raised to power minus s. Then we had minus of this Laplace transform, so minus, and then this quantity. So finally we get minus 1 over s pi square by 8s plus pi by 2s square, and then e raised to power minus pi s by 2. And then we again had this e raised to power, here it will be minus pi s by 2. 1 over 1 plus s square. The answer. This is a Laplace transform of this whole function. So in this way, we can convert any piecewise function into an equivalent single function in terms of Heaviside functions, and then we can find the Laplace transform. So now the question is you have to find inverse Laplace transform. Transform is already given. You have to find inverse of it. So s square plus pi square plus e raised to power minus 2s over s square plus pi square plus e raised to power minus 3s over s plus 2 to the whole square. Yes, can you find inverse Laplace transform of f of s? Yes, anyone? Please do that. So we have to apply first shifting theorem and second shifting theorem, both of. Can you tell me what will be the inverse Laplace transform of this first term? Anyone? What is the value of, so whenever we apply second shifting theorem, so we multiply with e raised to power minus as. So this is something like e raised to power minus as, and a is 1 here. So what was the second shifting theorem? The second shifting theorem is whenever you multiply with e raised to power minus as, your function will get shifted by a. So, and this quantity here is Laplace transform of sine, I think. Yeah, sine omega t is omega over s square plus omega square. So I can just multiply and divide with pi. So if you multiply and divide this term with pi, right, here, so then it becomes a over a square plus s square, right? So ideally, if this is your f of t, then I mean this is your original Laplace transform, then its inverse will be sine of pi t, right? Because if we have sine of pi t, its Laplace transform will be pi over s square plus pi square. So this is sine of pi t, but now it is multiplied with e raised to power minus as. So we have to apply this form of Laplace transform because here there is no t plus a. So here there is only f of s. This f of s is multiplied with e raised to power minus as. So then we will have u of t minus a, f of t minus a. So 1 over pi will be as it is, and then u of t minus 1 will be there because a is 1, and originally it was sine of pi t, but there is a second shifting in time, so it will be sine of pi t minus a, pi t, then pi t minus a, pi t minus 1. This will be the inverse Laplace transform of the first term. For the second term, again, same thing, but now we have 2 here. So A is 2. So then we have 1 over pi u of t minus 2. This is something. Just wait a minute. E is minus 3 as it is. Let me write it clearly. So now your A is 3, right? And 1 over s square. So Laplace transform of 1 over s square. I mean, Laplace transform of t is 1 over s square, right? But it is shifted. So I can just write it like, let me just rewrite it. F of e raised to minus 3s. So it is, your A is 3, because e raised to minus as, so A is 3. And then you have f of minus a is f of s, right? Um, Finally, your, but this is also shifted, so you have to apply first shifting theorem also here. So because this is your not 1 over s square, it is s plus 2. So this, firstly you have to apply first shifting theorem. So first shifting theorem was when you multiply your function with e raised power at, then the Laplace transform becomes uh, s plus a, right? So if you see here, if you multiply your function with e raised power at, then your Laplace transform becomes f of s minus a or plus a. It was, I have to confirm this. Just let me see. It is minus a. Okay. So how will we do it? Can we write it like t minus 3? So can we write it like this, 1 over this L of 1 over t, right? So let's say if it is only t, so Laplace transform is 1 over s square. Now if you multiply with e raised power at, this transform is 1 over s minus a, so s minus a to the whole square, right? Okay. Then it with the Heaviside function u of t minus b, let's say. Okay. I'm just shifting it once again. With Heaviside function, so I'm just doing it like this. So it was this function. Now I'm multiplying it with Heaviside function and shifting with the quantity t minus b, right? So I have to do it consistently over the whole thing. So finally, this will be e raised power minus bs over s minus a to the whole square, right? So your a has to be -2 then, and v has to be 3. Then we can write it like, if a is -2, b is 3, then e raised to power -2, t minus 3, then t minus 3, and u of t minus 3. So this will be your answer. You see how I have done it? I am explaining it again. So a Laplace transform of t will be 1 over s square. And then if you multiply this function with e raised to power at, then your first shifting theorem will be applicable. So then it will become f of s minus a, which is 1 over s minus a to the whole square. Then to this whole function, I'm applying multiplying with u of t minus b. So then everything will be t minus in terms of t minus b, because if you see here everything in terms of is in terms of t minus a. So at the place of a I'm using. So if I multiply everything in terms of t minus b, then it will be e raised to power minus a, e raised to power minus bs into f of s. So e raised to power minus bs I have multiplied, and f of s is as it is. Now if you compare this expression with this expression here, so then your b is 3 here and your a is -2, right? Because it is +2, so a has to be -2 here only, then minus minus will become plus. So your a is -2, b is 3. You just put in this function, so it will become e raised to power -2, t minus 3, and then t minus 3, and u of t minus 3. So this will be your final inverse of this function. Do you agree with me or not? First Laplace transform. Please ask if you have any questions or doubts. Right. So here we have applied both first shifting and second shifting theorem, and that's how you have to do it. I mean, if you practice enough, you can easily understand that it is e raised power. So this is going to be your second shifting variable, which is second shifting constant, which is 3, and this is going to be your first shifting constant, which is -2. Okay. And then you can explicitly also you can try it like this. If you're not getting how to do it, then you can start from a simple function and then try to reduce it. Okay, then now we are going to deal with something known as short impulse functions. Impulse function is in heaviside functions, you had sudden you were switching on something like suddenly. But in short impulse function, there will be a signal for a very short interval of time, or there will be a force acting on tennis, and you hit the tennis ball with the racket. So the impact of the tennis ball on the racket will be for a very short interval of time, right? Or the force applied by the tennis ball on the racket will be for a very short interval of time. So that is not known as an impulse force, which is applied for a very short interval of time. Or for example, you are sitting in an aeroplane and the aeroplane is landing and the landing is a bit hard. And the landing gears of the aeroplane strikes the ground suddenly. So the force that will act on the landing gears will be for a very short interval of time, that huge amount of force. Similarly, let's say you are blowing something with a hammer. So when you hammer something, so the force applied by the hammer on the object will be for a very short interval of time. That will also be known as impulse force. Or let's say you would have watched the Titanic movie. So let's say Titanic ship is struck by some glacier. So then when the glacier will strike to the ship, that also will be the impact force will be for a very short interval of time, but the magnitude will be very high. Examples of short impulse functions. So let me just write it. Rear plane a structure hit by hammer blow. Ship hit by glacier. Tennis ball. I mean, there are several other examples. I'm just giving few. So I'm just defining what is impulse function. So let's say this function is denoted by f of k and t minus a. This function will be equal to 1 by k, right? When t is going from a to a plus k. 0 otherwise. What do I mean if I plot it on graph? So it will look something like this. So let's say this f of subscript k t minus a, and here you have this going from a to a plus k, and for that interval its magnitude is 1 by k, right? Here it is 1 by k. And if you integrate this, so integration will be from a to a plus k, because it is it is 0. So and then I get that in that interval and dt. So its value, if you integrate this, it will be 1, because this interval length is also 1 and height is 1 by k. So area under the curve will be 1. Similarly, let's say if this k is approaching to 0. So this k approaching to 0 means I want to say is let this k is approaching to 0 and f of k. I want to evaluate f of k when k is approaching to 0. So then it is denoted as direct delta function. So del of t minus a, and it is also, we can also write it like limit t approaches to 0 f of k. So if you see from this interval, since k is approaching to 0, this quantity will approach to infinity, because this is 1 by k. But area under the curve will still be 1, because um, very large value, but then this is a very small value. So because this integration area under the curve is not dependent on k. Whatever is the value of k, you're going to get. So So I'm just defining direct delta function. So it is infinity if t equal to a and 0 otherwise. The definition of direct delta function, and obviously it is active for a very short interval of time. So now let's say, can you tell me what is the value of 0 to infinity g of t del t minus a dt? Yeah, what will be the value of this integral? Can you tell me? U of t with del of t minus a. So it is 0 everywhere, right? Other than a. So it may be, I think I made some mistake. It is correct. So what I want to say is this function is in 0 everywhere. So it will only be active at t is equal to a, right? Multiplying with g of t and then you are integrating. A bit hard to visualize this result, but I mean this is infinity, but this is finite. So multiplied together will give this result. You can check it numerically. You just take some large number, okay? But then you have to satisfy this property also. Mathematically, this is written, okay? If you multiply any function with direct delta function and integrate from 0 to infinity, then its value is equal to g of a. Anyway, so try to find out the Laplace transform of direct delta function. Firstly, we'll start with finding Laplace transform of f of k. So k was nothing but it was 1 over k. Let me just write in terms of Heaviside functions. 1 over k u of it is active only from a to a plus k and its value is 1 over k, right? So when t is less than a, it is 0, right? So this quantity will be 0 when t is less than a and it will be 1 when t is greater than a. Bring it with t of minus of a plus k. So because when t is less than a, both the quantities will be 0. When t will be greater than a, this will be 1. This will still be 0 because a plus k. But when t will be greater than a plus k, then this will also be 1, this will also be 1, again this will be 0. So this is 1 by k only in the interval when t is greater than a and less than a plus k. So then the Laplace transform of 1 over k u of t minus a is a raised power minus a s over s, right? And then u of t minus ak will be e raised power minus a plus k s over s, right? So this will be the Laplace transform of f of k. So I'm just rearranging few terms. ks, right? We can write it like this. And now I'm taking e raised power minus as also common. So finally we'll be left with 1 minus e raised power minus ks over ks. So this is Laplace transform for f of k. Limit when k is approaching to 0, then this becomes Laplace transform of direct delta function only when k approaching to 0. So then this becomes that k is approaching to 0. So this will become, if you put 0 here, so it will become 1 minus 1, 0 over 0. So it becomes a 0 by 0 form, which is an indeterminate form. So you have to apply L'Hopital rule. So if you apply L'Hopital rule, so if you have to differentiate numerator and denominator both with respect to k. So if you do that, so this is nothing but Laplace transform of direct delta function. If you differentiate both numerator and denominator with respect to k, if you do that, so finally you will get e raised power differentiation of 1 will be 0 and differentiation of this will be minus k, e raised power minus ks, and then differentiation of k will be 1, so that will be s, and then again limit k equals to 0, right? So okay, I think this will be minus s not minus k because we are differentiating with respect to k. So now this s and s will get cancelled, right? Finally we'll get e raised power minus as and then e raised power minus ks and limit k approaches to 0. So if limit k is approaching to 0, so this will be 1. Finally we'll get e raised power minus as. So then we can say that Laplace transform of e raised power minus as. Solving a problem of mass spring system under a square wave. Firstly, we will take a mass spring system and we will apply a force equal to square wave and then we will apply a impulsive force and see what will be the difference in output. So we will take that in the next class. I'm just writing the equation. Equation is y plus 3y prime plus 2y is equal to t minus 2 and the boundary conditions are y of 0 is 0. If you see this function is nothing but if you plot this function, so I'm just plotting you. So when t is less than 1, this is also 0, this is also 0. 1 everywhere, less than 1, everything is 0. And then when t is greater than 1, this is 1, this is 0. And then when t is greater than 2, both are 1, so both will be 0. Finally, this value will be 1. So now, so this is a differential equation of spring and mass system. So you have a spring and a mass, and then you are applying some force on the mass. So it will vibrate, right? And it has some damping also. So spring and mass system subjected to this force. So force is applied and then removed. So it's like a free vibration with damping. So like for example, you so tires of the bike has, I mean the shockers of the bike has both spring and mass, spring and damper. And if you give a small force to your tire and then leave it, then it will vibrate and the vibrations will damp out and it will come to rest. This force is given for 1 second, you can say 1 to 2. So it's for 1 second. And then we will give a force, we will give an impulse force also. The next class we will see what is the difference when we apply a force for 1 second and remove it, and then if we give a small impulse force, then what is the difference in responses of this spring mass system. Okay, so we will stop here for today, and can we schedule the next class tomorrow? Schedule tomorrow on the same time at 8 p.m. Yes. Just want to discuss these two examples in tomorrow's class. It's really important.